We're ready to start talking about complexity of algorithms, orders of growth. And we're going to do that using something we refer to as big O notation. Comes from the Greek symbol omicron, which was the symbol that was used to measure it, which is why we will sometimes also write it as O, and we'll be using that notation. And what big O notation is going to do is measure an upper bound on the asymptotic growth of complexity. So asymptotic means as the problem input size gets really big, what is the behavior? And how do I put a bound on that, an upper bound on that that lets me describe that class of behavior? And obviously I'd like as good an upper bound as I can get. Rather than just seeing every problem as exponential, I'd like to say, no, this is inherently a quadratic problem, or this is inherently a linear problem. Big O notation is going to describe the worst case, as we've already said. And that's because the worst case can occur often, and it's usually the bottleneck in when a program runs. So I'm going to talk about what's the worst case behavior when I put that upper bound on it. And I want to express the rate of growth of a program, as I said earlier, relative to the input size. Finally, rather than using timing, I'm going to do this by evaluating the algorithm, not the machine or the particular implementation inside of it. And so big O notation is going to be our way of describing the asymptotic behavior of algorithms. Let's look at an example of what big O means. And I'm going to do this with a procedure you've seen before. This is computing factorial in an iterative fashion. So how do I do it? I set up a variable answer to 1, and then I run through a loop where basically I let n start at 1, and I keep doing that until I get to, let me say it again. Let's look at an example of this, and we're going to do it with factorial iter. We've seen this before. We're going to set up answer to be the value 1, and then basically we're going to multiply answer by n, decrease it by 1, and keep doing that until we get down to the point where n is equal to 1, and then we're going to return the answer. So it computes factorial, and I could ask, so how many steps are there here? And in fact, what do I have? Well, I know that there are 2 steps right there, because literally what I'm doing is setting, if you like, n temp to n minus 1 and then n to temp as I do this, or if you like, doing both an addition and a reset. But what we can see is inside of this expression, I have the following. I have 1 step there. I have a loop here that I'm going to go through n times, and inside of that loop, I have actually 5 steps. The test, 2 steps there, 2 steps there. So I've got 5 steps, and I'm going to do that n times. So I've got find n operations, and then finally I'm going to return answer, which gives me 1 more. So the expression for the number of operations independent of the machine is 1 plus 5n plus 1, or 5n plus 2. I want to know what's the worst case behavior. And so as n gets really large, the fact that I got 2 extra steps becomes irrelevant. And that says that I can ignore the additive constants, the 2 ones. The fact that it's 5n as opposed to 7n or 3n as n gets large really also doesn't matter. Practically, it'll be a little bit difference in time, but as an asymptotic behavior, it really doesn't matter. And so in fact, I will say that this is order n. I ignore the additive constants, I ignore that multiplicative constant, and I basically say this is a linear or order n algorithm. So that says when I get expressions for the number of steps inside of a particular computation, I'm going to drop the constants, and I'm going to drop the multiplicative factors, and I'm just going to focus on the dominant terms. So if I had an algorithm that had the number of steps shown in that first example, I'm going to say that's order n squared. And if you think about it, as it says, as n gets really large, n squared is going to be much, much more dominant than the 2n factor. And so really this grows as n squared. Even if it's n squared plus 100,000 n, plus a really large constant, we still say this is order n squared, because asymptotically as n gets really big, that's the dominant term. For the third one, it's order n, because n grows more rapidly than log n. And as a consequence, this, as things get really large, is the dominant term. For the third one, we'd say it's order n log n. And for the last one, it's order 3n. May look a little weird. N to the 30th is a big number, but as n gets really big, this grows much more rapidly than this. And so we will say the dominant term here is an exponential in 3, as opposed to a polynomial of n to the 30th power. So these are going to show us how we simplified the expressions, and you can now see what we'd like to do. Given an algorithm, we're We're going to count the number of operations as best we can as a function of size of input. And then we're going to ask, what's the dominant term here? Where's the bottleneck? What's the worst case behavior? And that's going to let us characterize the order of growth. We've already seen these examples. These are the kinds of behaviors we're going to look for. Constant, written as order 1. Logarithmic, written as order log n. Linear, written as ON. Log linear, written as O of n log n. Polynomial, written as order n to the c. And I don't really care that much what the c is, but I'll at least distinguish, is this quadratic versus cubic versus something else? And finally, exponential. Does it grow as c to the n as opposed to n to the c? And if you don't understand the difference between those two, write a little program and look at some difference in values between n to the c and c to the n. Pick c, for example, as a 2 or a 3 and see how differently these change. Ideally, I'd like an algorithm that is as close to this point in the hierarchy as possible, because the higher up I am in this hierarchy, the more efficient the algorithm is. So, a couple of statements about this, and then we're going to look at some examples. One of the things I want to be able to do, as I said, is analyze the programs and talk about their complexity. And I'm going to combine complexity classes. I'm going to analyze statements inside the functions and then apply some rules and focus on the dominant term. So here are two things to look at. The first one we can call the law of addition for big O notation. And we use it with sequential statements. So if I have a piece of code followed by another piece of code, I could get the order of growth of the first piece of code, the complexity of it, and then the second one. And then I can talk about the sum of those being the order of growth of the overall combination. So for example, if I have two little loops as I've shown down here, the first one is order n, the second one is order n squared. The overall order is order n plus n squared, and as a consequence, the law of addition says that the order I want is just n squared because that's the dominant term. It says I can add up the complexity in order to do the analysis. And that makes sense. This is going to take much longer than that as n gets really big. So I've got a law of addition for analyzing these pieces. I have a second one, a law of multiplication for big order, and we use that when we have nested statements or loops. So in this case, if I have something that has a particular function, and I've got another one that I'm going to do inside of it, the order of growth of that multiplication is the order of growth of those two functions multiplied together. Another way of saying it is if I have two loops, one inside the other, so I'm going to loop over this loop, and inside of there I'm going to do a second one, then I have an order of growth n for the interior part, and an order of growth n for the exterior part, and that is the same as having an order of growth of the product. That is, I'm bringing this multiplication inside the notation, and we say this is n squared. Another way of saying it is, it's because that outer loop is done n times, and the inner loop also does n times, and since we do the inner loop n times for every version of the outer loop, it's n times n, or n squared times, in terms of execution for this particular kind of example. So I can analyze loops or nested statements, looking at what does it take the inner part, and then what does it take, how many times do I do that inner part in the outer part, multiplying that complexity together. And we saw with addition, when I have sequential things, I'm going to add the orders of growth together and then do the analysis.